Okay, so let me start once again. Yeah, so so in a typical communication scenario, my signal is composed from light pulses that contain some average number of signal photons, ns. This is after losses. I have some additive noise quantified by the average number of photons per pulse, per time bin, and then I make a measurement on the whole signal. And now, if you want to know what is the capacity of such a scheme, you can refer to the well-known classical result known as Shannon-Hartley capacity limit that tells you that this capacity is given by the logarithm of 1 plus number of your signal photons divided by the total noise. So why I'm saying here total noise? Well, this noise is just given by, I mean, the additive noise that I added here is given by this number, and I have also one here. So that's because in order to derive this formula, you need to assume Gaussian modulation of coherent states and also heterodyne detection of two field quadratures at the output. And as you probably know, heterodyne detection is shot noise limited. And this shot noise is exactly this one that appears here in the denominator. So the total noise is just 1 plus the number of your noisy photons. Yeah. So if you look right now at this formula, you see that it depends just on the signal to noise ratio. Yeah. So you divide the number of your signal photons by the total noise. Okay. So this is this classical result. But as you probably also know, there is also this classical capacity limit, which is also known sometimes by the Holevo limit or Gordon-Holevo limit. So this is because Gordon was, I think, the first person to come up with this formula, although with a very specific case, and it was using a lot of hand waving. It was back in the 60s. So yeah, you can write the result for, I mean, you can write the formula for the capacity. And what is important here is that this is optimized over all conceivable physical measurements allowed by quantum mechanics. Yeah, so this includes like very exotic quantum strategies, collective detection, whatever you can come up with. And this formula is already optimized over those measurements, and also over all possible modulations. So yeah, so as I said, you assume here a general measurement. So you do not have any noise contribution from the measurement here in this formula. And the second thing that is important here is that if you look at this, then you see that there is more than a signal to noise ratio to this bound. Yeah, it depends not on the ratio of signal and noise, but on the signal and noise separately. Yeah, so there is more to that than just the ratio. Okay, so we have this bound, and we can right now say that, well, this Gordon-Holevo limit is of course larger than Shannon-Hartley capacity because we optimized over all possible measurements. So yeah, let's put all our money into those quantum receivers, quantum detection strategies, because they will give us a lot of enhancement. Let's investigate them, let's build them. But in fact, well, it's not really obvious if those quantum strategies offer you any advantage. Yeah? So if you ask this question, do quantum strategies offer an advantage? The answer is that, well, it depends. And on what it depends, I will try to tell you. So as a first example, let us consider strong noise limit. So if you expand your Gordon-Holevo limit around the value of around large noises, then what you get is that this limit coincides with the Shannon capacity up to some small corrections. Yeah? So, and this happens irrespectively of the signal strength. Yeah? So no matter how strong is your signal, if a lot of noise, you will always be limited by this classical strategy. Yeah. So like quantum receivers here are useless. Secondly, okay, let's say that my noise is weak, or I have no noise. So I can investigate the regime of strong signal. And once again, I can make an expansion, and I can show that this Gordon-Holevo bound is equal to this classical Shannon strategy plus 1 nut. Yeah, so 1 nut is like 1.4 bits. So I have advantage here. It's quantified by this 1 nut, but you see, I mean, it's just a constant number. Yeah, so it's small if you are operating in the strong signal regime. So right now, if you plot those limits here, and as a function of the signal strength, you will get the following result. So yeah, here you have this Gordon-Holevo bound. Here you have this Shannon limit coming from the heterodyne measurement. And for for strong signals, you see that, well, those two curves are parallel, and the distance between them is just a constant number, yeah, 1.44 bits. So we can conclude here that, well, heterodyne measurement is the best that you can do here. Yeah? You do not need to use any quantum strategies. But yeah, you may argue that those cases that I showed you here, the strong noise case especially, are not particularly interesting here, because why would I make a communication if I have a strong noise? Yeah, certainly the performance then would be weak. So what I would try to convince you that this is not the case. There are very important scenarios in which you have a strong noise, and I guess the most important one are multispan amplified fiber links. So let's imagine I have a fiber link of some length. This distance is large. Like, let's say it's between Europe and America, so it's like a few thousand of kilometers. And I put amplifiers in this fiber. Why I need to put amplifiers? Well, because if I would have just a bare fiber, then attenuation of my signal here would cause that I would not see anything after a few hundreds of kilometers. Yeah, so it wouldn't be possible to communicate anything. So I need to use those amplifiers to amplify my signal in order to be able to see it. But now those amplifiers can introduce noise. So if I use phase-insensitive amplifiers, like quantum-limited phase-insensitive amplifiers, they introduce noise. And this noise, it's important here that the noise introduced by a particular amplifier is then amplified by each subsequent amplifier. Yeah. So at the end, I can have a lot of noise. Yeah, but still I can optimize the capacity, both this Shannon bound and this Holevo bound, over the gains of my amplifiers, over locations, under some certain reasonable conditions. So here I assume that the total power in each point of my link is cannot exceed the input power. So if you do it, then you end up with the following plot. So this is a plot of capacity as a function of distance. So if you have no amplifiers, then you see that, well, you have a large quantum advantage. Yeah, so Holevo bound is much larger than the Shannon limit, but also you cannot communicate for distances larger than like 200 kilometers, let's say. And now, if you start to increase the number of amplifiers in your link, you see that you can communicate over longer and longer distances in this fiber, but also this quantum advantage disappears. Yeah, so if you go to the distributed amplification case, so you have like infinite number of them, well, there's still some very small advantage here, but it's barely visible for more than 300 kilometers, and asymptotically it would vanish. Yeah. So yeah, heterodyne measurement here is the only thing that you need to care about, yeah, because this Holevo bound is equal to the Shannon bound. Yeah, but you can argue that, well, I introduced noise here because I use those noisy amplifiers, even though they are just quantum limited. So maybe I can come up with better strategy. Well, yeah, I can use here phase-sensitive noiseless amplifiers. So ideal phase-sensitive amplifier is noiseless. Yeah, it does not introduce any noise. And once again, I can do optimization like before. And if I do it, I will get a following plot. So okay, you can notice that the scale here changed. Yes, this is just in order for this to be visible. I mean, the result is very similar. Yeah, this Holevo bound also coincides with the Shannon bound for large number of amplifiers. Yeah? So we can conclude that even with those phase-sensitive noiseless amplifiers, I still cannot do much better than with heterodyne detection. And why is it like that? So this is because even though my amplifier is noiseless, I have losses in each of those spans here. Yeah. And since I have losses, then there are some vacuum fluctuations that enter my signal, and those vacuum fluctuations are then amplified by those phase-sensitive amplifiers. So even though I have, well, if you look at it like naively, I have no additive noise here, then by this interaction between losses and this phase-sensitive noiseless amplification, I will have additive noise. And well, if you look at this plot, this noise is quite strong. Yeah. So yeah, we can conclude that heterodyne measurement attains this Gordon-Level bound in this important case of amplified links. I mean, okay, you still have some advantage, but for short distances, and this advantage is very small. Yeah, so this is in a sense a negative result. Yeah, that you do not need to care about any quantum strategies for fiber links. But I told you that I'll give you some examples of instances when quantum strategies can help. So yeah, so if you look right now at this picture, yeah, I showed it before. You have this Gordon-Level limit. We have this Shannon 2-quadrature limit. I mean, okay, and we can also derive the Shannon limit for 1 quadrature. So we investigated what happens when you have a strong noise. Yeah, so for strong signal. So for strong signal, you have just this one not constant advantage. But you see here that in this limit of weak signals, yeah, I can have better measurement than this 2-quadrature measurement. Yeah, simply I can use homodyne measurement, so I can measure just a single quadrature. And if I derive Shannon bound for this single quadrature, I can exceed this 2-quadrature bound. Yeah. So maybe it's like that in this weak power limit, this Gordon-Level bound is even better than those classical ones. And maybe I can get there using various quantum measurements. Yeah. So right now we will be investigating this regime. So this is weak signal regime. And this is a typical regime for satellite communication. Yeah, so if you have satellite, it's very far away. So you have strong losses. And also since the satellite has some limited power budget, you cannot use very powerful laser on it. Yeah. So you have quite weak source. Okay, maybe not so weak, but the signal that you will receive will be very, very weak because the power of your source is limited and you have very strong losses. And this is in particular relevant for deep space missions. So if you think about satellite going to Mars or, I don't know, maybe even farther, then you are really in this weak signal regime. Okay. So in this photon-starved communication, the good quantity to look at is not the rate or capacity, it's rather the photon information efficiency, which is defined as number of bits that you can transmit using a single photon. So in order to get this photon information efficiency, this PIE, you just need to divide your rate or capacity by the average number of signal photons per time slot. And if you plot right now this PIE in this weak signal regime, you will get the following plot. So you see here that those Shannon limits, they will give you a constant value, both for single and 2-quadrature detection. Whereas this Gordon-Level limit, it grows. Yeah. So you have a large gap here for weak signals. And this is in the noiseless case. So the question right now is, what is the size of this gap? Okay, so you can calculate those photon information efficiencies, and you can get that for the single, for the 2-quadrature measurement, this PIE is equal to 1 NAT. For 2-quadrature measurements is equal, sorry, for single quadrature measurements is equal to 2 NAT. And for this Gordon-Level limit, it grows with decreasing signal strength. Yeah. So you can make this gap as large as you want just by going to weaker signals. Yeah. So you see that in this weak power regime, those quantum strategies potentially give you a large advantage over classical ones. So now the question is how you can get to this Gordon-Level limit here. So the strategy is following. So you need to encode your signal using pulse position modulation. So you have you encode your signal in words, in frames composed of m time slots, and only one of those time slots is occupied by a light pulse. Yeah, and then at the output, you are just making direct detection. So either you will see a click here in a particular time bin, or you will have an erasure event. And now, if you plot the photon information efficiency for such strategy, you will get the following result. Yeah, so here I'm increasing the PPM order, so the size of this PPM frame, the number of time bins in a single frame. Yeah, so you see here that if I increase this number, I can get closer to this Gordon-Hall level limit in the weak signal regime. Yeah, so the lower my signal is, the larger frames I need to take, larger PPM orders. Okay, so now you can also do this in the noisy case, provided your noise is not too strong. Yeah, and you can get very similar results. Although this time this Gordon-Hall level limit it saturates at some particular value, but still your advantage over classical strategies can be large, particularly for low noises. The only difference here, if you include noise, is that you need to also care about multiple click events. So you need to use more sophisticated strategies. Instead of direct detection, you need to have photon resolution, and you need to use more sophisticated decoding methods like soft decoding. But nevertheless, you can do this. Okay. So why I'm telling you about this? Yeah, because this does not seem very quantum. Yeah, you are using direct detection, and well, you are just encoding your information in a position of light pulse. Well, that's because if you look at this picture, there is a problem, and the problem is that if you have a weak signal, you need to have large PPM order. Yeah, so you need to have large M. So if NS right now is the average number of photons per time bin, so this is what enters the formula for capacity. Even if NS is very weak, then M can be large, and the number of photons that is contained in a single light pulse can be very, very large. Yeah. So even if NS is very, very small, yeah, it's average over all those time bins, yeah, and all of them except of one contain no photons. So I need to compress all my power into a single light pulse, and well, in particular, in some cases, it can be very strong. So I need to have large instantaneous power, and this may be very problematic if you think about satellites, yeah, because satellite has some limited power budget, and well, I cannot spend like, I don't know, 1,000 watts on a single light pulse. Yeah, I mean, it's impossible. So how to overcome this issue? So yeah, so we know that we know what to do for this pulse position modulation. But on the other hand, you would like to have a signal that has uniform strength in all time bins. Yeah, so somehow we would like to either make a detection on such signals where each time bin has small number of photons, or somehow to convert this modulation to this modulation where I have information encoded in position of my light pulse. And well, how to do this? Well, you need to use what is known as super additivity of accessible information. So the trick is that if you use right now collective detection on those light pulses that contain very small, very weak signals, and they are distributed uniformly, then if you use this collective detection, you may prove that you can get more information from the joint detection than just individual detection of each light pulse. So there are some, you can derive some joint receivers. So I would not give you details here. Michał Jachura in the next talk will tell you how to construct those receivers. But I would just tell you that you can compress your signal iteratively just by optical methods, yeah? By optical devices that really exist in a lab, to this pulse position modulation, and this is done at the receiver side, yeah, so on Earth. So you do not need to care about what happens on the satellite, yeah. You just need to buy more expensive receiver. And well, we know what to do with this pulse position modulation. We are just making direct detection. So yeah, so this, in a sense, tells you that there are some instances where this collective detection is more practical than like classical strategies, yeah? Because, well, it's easier to invest money on your single receiver that sits on Earth, yeah? And just you need to have more more sophisticated telescope, more sophisticated detection method, then just put like very strong lasers on satellites, which, well, it's impossible anyway. Yeah. So by this I would like to conclude. So yeah, quantum advantage can be observed only for low noise. If you go to low power limit, then you can observe big quantum advantage. And well, as I said, there might be cases in which quantum enhanced receivers are more practical than classical ones, but they are like those extreme cases of satellite missions. Yeah, and by this, I would like to thank you.
Great, thank you, Marcin. As you know, we have 3 questions, and the first one will be what you think will be the main first use case for entanglement-assisted communication networks. Do you have an opinion?
Well, so I think that entanglement-assisted communication networks wouldn't appear anytime soon. But when they appear, the first use case may be to entangled quantum sensors. Yeah, because I mean, quantum sensors are maybe not already hitting the market, but well, they are the closest thing to have real applications. Yeah, so I think this would be the use case.
And is there a way you see you could contribute to realizing the use case? And if there is such a thing you could do in your field, what's the main challenge?
So what's the main challenge so could you repeat? Because
so basically, let's assume we want to realize these quantum sensors. Then what's the main challenge where you are expert on the challenge?
Well, okay, I don't really know what would be the main challenge. I mean, so there are already quantum sensors that are used for sensing magnetic fields. I guess people try to use them to make gravitational field also. So, well, you can do this, and then there is known result that if you have entanglement in metrology, you can usually estimate parameters better. Yeah. So, well, this is just my intuition. I don't have anything in my mind on this subject. Yeah.
Okay, thanks. And the contribution to 6G?
Sorry? The contribution to 6G. So I think that if there would be any quantum technologies contributions to 6G, this would be rather in the form of like signal processing. Yeah, you can have like maybe you can use quantum technology to have better filters, something like that. I wouldn't expect any entanglement or something like that in 6G.
Great. Then let's thank the speaker again.